Hello, everyone. In our work, we tackled the problem of unpaired domain transfer, which is crucial in the field of medical imaging in the absence of in vivo labeled data. There is a lot of impressive prior work, for example, with laparoscopic or MR images that leveraged real data to make their simulations more realistic. But we wanted to take a look at spectral imaging modalities, meaning imaging modalities using multiple wavelengths. We applied our method to two different modalities, but in this talk, I will focus on photoacoustic tomography. It is an emerging non-ionizing technique that utilizes both the way photons propagate in tissue and the way ultrasound pressure waves propagate in tissue. This brings a lot of challenges. For example, it has two ill-posed problems for signal reconstruction, and since photon absorption depends on the wavelengths, it's spectrally very complex. This means that after we transfer a simulated image to the real domain, physics has to be conserved and the spectra have to be consistent. So just nice-looking images are not enough for us. In this field, the CycleGAN has been a great success story, as a vast majority of state-of-the-art methods still use the cycle consistency loss in some way, so that an input that was passed through the generators for each domain has to be reconstructed to the input image again. GANs in general, but also the CycleGAN, however, can suffer from mode collapse, artifacts, and unstable training. Especially mode collapse can be difficult to overcome, which is why we address this problem in our work. We propose conditional invertible neural networks, or cINNs, for domain transfer. There, an input X can be passed through a cINN with a specific condition C to a Gaussian latent space variable Z. If we now input Z from the other side with the same condition C, the output is per definition again X. This way, we can guarantee exact cycle consistency without needing a specific loss term. Furthermore, since there is no information loss in the cINN, we can use a maximum likelihood training that optimizes the likelihood of Z being Gaussian. In comparison, the evidence lower bound loss used by variational autoencoders only yields a lower bound estimate of this likelihood. So what does our model look like? It is built of multiple scales of conditional coupling blocks, here CC. One coupling block comprises two neural networks or subnets that can be, for example, 2D or 3D convolutional neural networks or fully connected ones. Coupling blocks are designed such that each one is invertible on its own, thus ensuring exact cycle consistency. Additionally, a condition can be concatenated to the input of each block. In our case, the domain or the domain simulation or real, as well as tissue labels for the simulations, where we have the ground truth and a random tissue label for unlabeled real data. This way, a sample of each domain can be encoded to the shared Gaussian latent space on the right with their corresponding conditions. And here, the maximum likelihood training prevents mode collapse. We added also two discriminators, one for each domain, so that we can choose to add adversarial training to the loss function for high visual image quality. For inference, a simulated image is encoded into the latent space with its corresponding tissue and domain labels, and subsequently decoded with the original tissue label, but now with the real domain condition. For photoacoustic tomography, images, simulations, and real images look like this. Not only look they visually different, but also their spectra are not overlapping very well. If we now input the simulated image to our network, thus encoding it into the latent space and then decode it to the real domain, it looks like this, for example. For non-photoacoustic experts, this might look similar, but key characteristic features look more realistic now, such as the skin at the top. To ensure that the underlying physics is still valid, we will call which we call spectral consistency. We also look at the new spectra, and we can see that the green cINN transferred data now nicely overlaps with the real data. So we can learn characteristic features on the real domain while still staying spectrally consistent. So does this increased visual realism also help us with our downstream task of classifying vessels for photoacoustic tomography, where we input the whole image to the neural network, as well as for organ classification and hyperspectral imaging, where we input only a single pixel spectrum? Yes, it does. And this holds true for both imaging modalities. We can also see a benefit compared to the widely used baseline method, UNIT, which is based on CycleGANs. So what are the key takeaways from our work? Our proposed cINN is an entirely new domain transfer method that guarantees exact cycle consistency. It avoids mode collapse with maximum likelihood training and utilizes tissue labels for spectral consistency. One of the major limitations of the method is the high dimensionality of the parameter space as a consequence of the information conservation. Let's talk about it at the poster.